Okay, so last time when we did standard deviation, the variance, I was right to put the bracket over the whole bullet point where you add the squared deviations and you divide by n minus 1. The variance in this case is 1.8. So it is the sum of the squared deviations divided by n minus 1. So variance is 1.8. It is the whole bullet point. So that means where I just highlighted the numerator, it actually is the numerator and the denominator. That was the mistake that I made. No. When you root it, it's the standard deviation. Before you root it, it's the variance. Let me go there in just a second. On the bottom of your table, I wrote variance here. I changed it to sum. Because this is not the variance, it's just the sum. And then I'll go to that problem in the CFU to check that we're all on the same page. So, in the actual CFU where you have to calculate it, the variance is 1.3 with a bar over it. So it's the 4 divided by n minus 1. So it's 1.3. And then you root that and it's the standard deviation. So the variance is the radicand. It goes underneath the root. So it might be clearer if I did this. So once you root the variance, that's your standard deviation. That was all that I needed to correct for you. Okay, so then today we're moving into z-scores, and depending on what teacher you had for Math 3, this could potentially sound very familiar to you. So z-scores follows standard deviation because a z-score tells you how far and in what direction an observation lies in terms of standard deviation. So I'm going to highlight the most important parts on that definition. So a z-score tells us how many standard deviations and in what direction an observation falls. So we can take any piece of data in the data set and write it in terms of how many standard deviations away from the mean it is. So observations that are smaller than the mean will have a negative z-score because it's below the mean. And observations that are larger than the mean will have a positive z-score. That's what tells you the direction. So here in the definition where it says it tells you how many and in what direction, the sign tells you the direction. So if it's negative, that means the direction is below the mean. If it's positive, that means the direction is above the mean. When we convert these observations from the original value to the values written as standard deviation, it's known as your z-score. Oh, I lied. It's known as standardizing. Standardizing. So I try to remember that because it's called a z-score and standardizing has a z. So when we take an observation, convert it to a z-score, it's called standardizing the value. our formula for all of our z-scores, and we're going to end up by the time we test using this formula a ton. You find your z-score by taking your observation. So this x here is the value of your observation. So this is your observation. It is an actual data value. It's a number from your data set. You subtract the mean, you divide it by the standard deviation. So for now, what that looks like for us is this middle fraction, x subtract x bar over sx, because we're going to have samples. Our data will be samples from the population. If for some reason we end up having exact population values, the formula is exactly the same, but the names of the different components are different. So instead of the mean being x bar, the mean is mu. And instead of the standard deviation being sx, it's sigma. But it works the same. Okay, so we jump right into an example. The figure below shows a dot plot of a class's height distribution along with summary statistics. So they not only give us the dot plot, but then they make things much easier for us by giving us all of the information we're interested in. We have a student in the class named Shelby. She is 65 inches tall, and we need to find and interpret her z-score. So the information that we need in order to do this is the mean of the class and the standard deviation of the class. And they're right next to each other right here. So I'm going to highlight that as soon as I find my highlighter. I want to use. So I need x bar and sx to do this calculation. Okay, so Shelby's z-score, I'm going to say z equals. X is her height. That's the observation we're interested in. So we say 65, subtract the mean of the class, 67, divided by the standard deviation of the class, 4.29. So on average, the class's height is about 4.29 inches away from the mean. So now we plug that in. Okay, I'm getting negative 0.46. So that's about half a standard deviation below the mean. So she's pretty close to the mean. Here's how we interpret it. Shelby's height is 0.46, and we don't put the negative on because we follow it up with standard deviations below the mean height of the class. So we don't put the negative on because we're using the word below in our interpretation. So Shelby's height is about half a standard deviation below the mean height. We're okay on this one? Yes.
So when they're grading it, do they want us to put below?
Yes. They want you to put the below. When they ask you to interpret, what they're essentially asking you to do is tell them in your own words what the z-score is. So you would need to say below to be able to describe to them that you have a true understanding that the negative on the standard deviation means it's below. Now, I don't think they'd mark you wrong if you said Shelby's height is negative 0.46 standard deviations below the mean. The most important part is getting the word below in there. So, okay, another student in the class, Ethan, is 74 inches tall. How tall is Ethan compared with the rest of the class? Give appropriate numerical evidence to support your answer. That just means show your z-score calculation. So they want to see you actually work out the z-score. So in this case, x has changed to 74. Our mean is still 67. our standard deviation is still 429. So you guys see if you can fill that one in now. You guys fill that one in. Let's go roughly 20. About 10. Five. So Ethan's z-score, or Ethan's height, is 1.63 standard deviations above the mean height of the class. So compared to the class, he's noticeably taller. Okay, last question on this side. Ethan is a member of the school's basketball team. The mean height of the players on the team is 76. So now instead of comparing Ethan or standardizing Ethan to the class, we're going to standardize him to the team. Ethan's height translates to a z-score of negative 0.85. So he's considerably taller than the class, but shorter than the mean of his team. What is the standard deviation of the team's height? So in our z-score formula, we have 4 variables. We have the z-value, or the z-score. We have the observation, the mean, and the standard deviation. And we're missing one of them. So they gave us the z-score, negative 0.85. They give us x, that's 74, that's Ethan's height. They give us the mean of the team, 76, and they want us to solve for standard deviation. So I would set that up in the z-score formula. Negative 0.85 equals 74 minus 76 divided by the value that we want to know. When you have an equation like this, to solve it, all that it looks like happens is that you switch these two values. By the time you do like the actual multiplying and dividing, what it looks like is that these two things switch. Because step number 1 is you would multiply both sides by standard deviation. Step number 2 would be to divide by standard deviation, or sorry, the z-score. So S sub x is really 74 minus 76 over negative 0.85. This is just the shortcut for solving. So I'm getting 235. What about you guys? Okay. If me saying that it switches is troubling you, over here to the side I can show you the actual work. So step number 1 is you would multiply both sides by Sx. And you would get negative 0.5. Sx is 74 minus 76. And then your last step would be to divide off the 0.85. So S sub x is just 74 minus 76 over the z-score. We're okay here? Yes? Okay. So one of the most valuable things about z-scores is that it allows us to make comparisons with or between different data sets. So the single season home run record for Major League Baseball teams has been set just 3 times since Babe Ruth. So Babe Ruth originally set it. He had 60 home runs in 1927. Roger Maris hit 61. He played in 1961, so about 30 years later. Mark McGwire hit 70. He played in 1998, so about 35 years later. And then Barry Bonds hit 73, and he played in 2001. Now, if we just look at the number of home runs, so in an absolute sense, Barry Bonds had the best performance out of all four of the players because he has the most home runs. He has 100, just kidding, he has 73. However, in a relative sense, this may not be true. So, baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including the quality of the batters and pitchers, the hardness of the baseball, the dimensions of the ballparks, and the possible use of performance-enhancing drugs. So, for instance, I'm pretty sure that Mark McGwire was accused of taking steroids in the time that he was hitting as many home runs as he was hitting. Further, as you can imagine, in the 1927s, conditions under which you play baseball are probably much different than the conditions they play in 2001. So it wouldn't really be fair to compare Babe Ruth to Mark McGwire because they played under different conditions. Does that make sense? So in order to make a fair comparison, we would see how well they did compared to everybody else that was playing at that time. So we need to standardize the scores for each player, and we need to standardize it to the data from when they were playing. So first guy here is Roger. This guy's Roger. This guy's Mark McGwire. This is Barry Bonds. And then our last one, Babe Ruth. So if we want to find the Z-score for Roger, so I'm going to call it Z sub R, Z-score for Roger. He is the second one down in the table. His number of home runs was 61. The mean number of home runs the year he played was 18.8. The standard deviation from when he played is 13.4. So these players were all over the place. Like the standard deviation on this data set is huge compared to the mean. Okay, so the Z-score for Roger, we plug that in. I think we get 3 something. 3.15. So this is definitely an outlier. Instead of using 1.5 times IQR, you could use standard deviations to determine an outlier. If it's more than 2 standard deviations, it's an outlier. So this is definitely an outlier. More than 3 standard deviations above the mean. Okay, now let's check it out for Mark. Mark hit, so he's the third row, 70. The year he played, the mean number of home runs was 20.7. And the standard deviation was 12.7. I think this one's another one in the 3s. 3.88. So he beats Roger. In a relative sense, Mark did a better job than Roger. Okay, Barry Bonds. Barry Bonds, I'm going to call his BB. Z of Barry Bonds. So Barry Bonds hit 73 in a year where the mean was 21.4 and the standard deviation was 13.2. What's that one? Okay, so he just barely beats Mark McGwire. Just barely. So far, Barry's in the lead. So you guys calculate Babe. Sounds like you guys are getting the right answer. So about 10. Three. So Babe Ruth is definitely the home run king. Babe Ruth was almost 5.5 standard deviations above the mean. So in a relative sense, who is the home run king? Babe Ruth. He was doing better given the conditions than the other three were. Are you guys okay with that conclusion? Yeah? Okay. So then the last problem is just another solve for a missing variable. In 2001, the same year that Bonds played, the same year that Bonds set the home run record, Arizona Diamondback Mark Grace's home run total had a standardized score of negative 0.48. Determine the number of home runs that he hit. So those four variables that we use in a z-score are z, x, x bar, standard deviation. They gave us z, negative 0.48. We also know the mean and the standard deviation from the table above. So in the year Barry Bonds played, the mean was 21.4. Standard deviation was 13.2. So if I plug all of that into the formula, I get negative 0.48 equals x minus x bar over standard deviation. To solve this equation, the first thing you do is multiply each side by 13.2. We're okay there? Whew. Those go away. I have negative 6.336 equals x minus 21.4. And now to isolate the x, I gotta move 21.4 over. How do I do that? Yep. So x for Mark Grace is 15.064. So Mark Grace hit about 15 home runs. That doesn't seem very good compared to Barry. It's not bad in terms of the mean, but compared to Barry, loser. Okay, so on your check for understanding on this, it's a mix of standard deviation and z-scores because they're very highly related. A z-score is how many standard deviations away an observation is. So your first 1, 2, 3, 4 problems are standard deviation. They could have been in the last assignment. Then in the middle, you have a bunch that are specifically z-score. And then toward the end, you have a couple more standard deviation ones. So it's a mix of the last 2 lessons. We'll be okay though, yeah? Okay. You have 40 minutes.